Welcome to the Walton Pie. Today we are going to talk about equivalence classes. Last time we talked about equivalence relations, and equivalence classes are very closely related to equivalence relations. In fact, they come out directly from a given equivalence relation. So if we have an equivalence relation R, we are going to use the little tilde, the squiggly dash, to denote the relationship between 2 points. So if the pair x comma y is in the equivalence relation R, we will write that x tilde y, meaning x relates to y. The definition of an equivalence class is this. For a given set A with an equivalence relation tilde and an element A in the set A, we will define the equivalence class of A by the set of all elements which relate to A. So, the class of A, the bracket A, is equal to the set of elements in A such that A relates to X, or where A comma X is an element of the relation. So, in this example, let's try and figure out what is the equivalence class of 3. So, we look to see what are all the things that relate to 3. Going through the relation, we find that we are going to have the pair 3 comma 3 and 3 comma 5. That tells us that 3 and 5 are going to be the elements in the equivalence class of 3, because those are the elements which relate to 3. Take a moment to try and figure out what the equivalence class of 2 is for this relation R. Hopefully that was enough time for you to go through and see that in this set, the equivalence classes are going to be, the equivalence class of 2 is the set containing 1, 2, and 4, because those are the elements that relate to 2, because we have the pair 2 comma 1, 2 comma 2, and 2 comma 4. Let's look at this last example. Let's see if we can figure out what is the equivalence class of 4. Here, we see that the only element that relates to 4 is itself. So the equivalence class of 4 is just the set containing 4. There is no other element in that equivalence class. There are also a few properties that come with equivalence classes. So, if we have bracket A denoting the equivalence class of A, the following 3 things are all equivalent. That means that either all of them are true or none of them are true. It is not possible for some to be true and some to be false. So, the following are equivalent. X relates to Y. The equivalence class of X intersected with the equivalence class of Y is not the empty set, meaning that there are some elements in both. And the third equivalent statement is that the equivalence class of X is equal to the equivalence class of Y. Let's go through each of these to show that they are, in fact, equivalent. So, let's show that if X relates to Y, then the equivalence class of X intersected with the equivalence class of Y is not the empty set. So let's assume that X relates to Y. That tells us that we have the pair X comma Y, and because tilde is an equivalence relation, that means we also must have x comma x, y comma x, and y comma y as a result of symmetry and reflexiveness of equivalence relations. That tells us that both x and y are in the equivalence class of x and the equivalence class of y, so the intersection must be non-empty. If we assume that the intersection of the equivalence class of x and the equivalence class of y is non-empty, then that means that there must be some element, let's call it z, in both of them. That tells us that for any a in the equivalence class of x and for any b in the equivalence class of y, we must have x relates to a relates to z, and z relates to b. Transitivity of equivalence relations tells us that that means that x must relate to b and b relates to x. That tells us that b, a generic element in the equivalence class of y, must be in the equivalence class of x. We also can do a very similar argument to show that A will relate to Y. So that tells us that everything in X is also going to be in Y. Or everything in the equivalence class of X, rather, is also in the equivalence class of Y. Because both of them, we have everything in the equivalence class of X is in the equivalence class of Y, and everything in the equivalence class of Y is in the equivalence class of X, that tells us that the two equivalence classes must be equal. Our last part of the proof is to show that if the equivalence classes are equal, then X relates to Y. This one is the simplest of the three, and we just have to state that because the equivalence class of X is equal to the equivalence class of Y, we know that Y must be in both the equivalence class of X and the equivalence class of Y. So, since Y is in the equivalence class of X, by the definition of equivalence classes, X must relate to Y. So, to recap, if we have an equivalence relation, it's going to generate equivalence classes. These equivalence classes have these three properties. All three of them are going to be all true or all false for any given two elements X and Y in our set A. X relates to Y, the class of X is equal to the class of Y, and the class of X intersected with the class of Y is non-empty, are all going to be true or they are all going to be false. I hope this video was helpful in explaining what equivalence classes were. If you had any questions, feel free to check out some of the other videos that I have done on this topic. Please like and subscribe, and I hope you have a wonderful day. Good luck!